Thank you. Okay, so you, if you go to the JuMP website on the page of this event, I've put the link of the repository where you can download all this. So it should be here. Notebooks. So you can press here and you can download the notebooks if you want to run them at the same time. Okay. So I start with this one. There are a few ones, so I don't know what time it will take, but so I've done the same thing as Juan Pablo for the introductory tutorial. I've set up a project where I have all the packages I need for all the tutorials, and you can just run this and it should be the same as on my computer. Okay, so in this notebook, I will briefly explain what's the relation between the MY backend that stores the problem and the JuMP model, how they interact. And in particular here, I talk about the constraints macro, how it works, and how does it translate to MY. So for instance, suppose you want to add a constraint x equals 1 minus y, when x and y are variables, right? So what you do is you create a model, you create two variables, and then you do this macro, x equals 1 minus y. And we'll see exactly what it does. There's very useful macro in Julia, macro expand, which tells you what code is executed for this macro. So valid model is not extremely important, just so that if model is not a JuMP model, it gives you a nice error message. So for example, if this is an integer, we say, oh, it's an integer, not a JuMP model. A lot of plugin. So one thing that the JuMP macro does, and is kind of important for performance, is that here, if you have a long sum of numbers, it will actually rewrite the expression, not doing plus, 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 and the base that plus method. It will rewrite it to be more efficient. So we'll see that. And then it computes, so it moves everything in the left-hand side. So it'll be x minus 1 plus y. And then it will say this x minus 1 plus y should belong to the set of the numbers equal to 0. So it creates this function, and then it adds the set equal to 0, and then it adds these constraints, okay? So let's break it down. So what it does, so I've just rewrite this like this so that it's clear what it does. So first, I say it builds the left-hand side. So to build the left-hand side, it first creates a val false, which means a 0 function in JuMP, when in the macro code at least. And then it's using this destructive add with reorder methods. So what this does basically is that we'd like to build the left-hand side efficiently. So we like to not create many intermediate functions. So basically what we'd like to do is we create an affine function and then we stuff everything in it. Instead of, if you do a affine expression plus a affine expression, is create a new one. And what you like to do is instead you modify the first one. So you create this function. Currently there is nothing. So we have val false, and then we'd like to add to this function the variable x. So what the result is a variable. Okay, so currently in the left-hand side, we just have a variable. Then we want to add to this variable the minus 1 times 1. So 1, it was because there was 1 in the right-hand side, and we multiply with minus 1 because we move it to the left-hand side. So, okay, so we have now an affine expression which is equal to x minus 1. And now we want to add y, when to move it from the right-hand side to the left-hand side. And so the naive approach would be multiply y by minus 1. So it creates an affine expression which is minus y, and then add it to the left-hand side by creating, again, a new affine expression. And then you will create two affine expressions. And that's what we try to avoid. So here, we try to say, in fact, what we want to add to this function is minus 1 times y. And so what you just want to do is add a term in the function, which is 1 times y. Okay, so here it will not allocate any new affine expression. If we just add in this affine expression, it will add a term, which is y with coefficient 1. Okay, so that's the reason why actually writing your sum inside the JuMP macros would be more efficient than writing your sum outside of the macros, because it's doing this rewriting. Okay, so now that we have the function, what does it do? So you have this function that should be equal to the set of all number equal to 0. And so from this function and this set, it creates a constraint object using this build constraint function. Okay, so the build function constraint function, it takes the function as set, and the first element is an error function. So basically, what the macro does, it's in this first context, like, okay, you've called this macro. It prefixes this error comes from. But if we just give the error function here, it's fine. So from this function and this set, it creates this scalar affine, the scalar constraints. And so in fact, when you have like, scalar constraint, a little detail is that the constant is moved back into the set. We always move the constant in the set. So it's no x plus y equals 1. Okay? But if you look here, we've not modified the model yet. We just create some constraint object, but the model is not even part of the argument of this function. So the model is not modified yet. We just created some constraint object. And then you can print the constraint object. It shows you the constraints, and that's what used in model printing. But if you actually want the constraint to be passed to the solver, you need to call add constraint. So add constraint, you give the model and just the constraint object, and it actually pass to the solver. And it gives you the reference of that constraint. Okay. And what's important here is that, so when you say add constraint, the constraint, it's passed to the MOI solver, so the MOI backend, and it's not stored by JuMP. So the constraint object you have built, it's just discarded. It's not, there is not a vector of constraint instead of JuMP. There is only one copy of the model inside the MOI backend. Okay, but you can query the constraint object back by doing constraint object of a reference. But it's going to ask the MOI backend, okay, what was the constraint? I don't remember. Then it's going to give me the affine expression in the set, and then it's going to build the constraint object again, and then it's going to show it. So when you print a JuMP model, for instance, that's what you have to do. You have to ask MOI what are all the constraints, what are all the functions of the constraint, all the sets, and then you rebuild the constraint object and then print. Okay, so to illustrate the fact that there is nothing stored in the JuMP side, we'll actually kind of trick the JuMP model. We will directly add a constraint to the MOI backend without using the JuMP model, and then the JuMP model will think that he added him himself. So we create, so by calling index of a JuMP variable, what you get is the MOI index, so in the index for the solver, basically. So you take the index of S and Y, you create a single variable function so that you can actually do operation on them. So you do 0.5 times the variable X minus Y, and you say this should be equal to 2.0. And then you add this constraint directly to the backend. So backend of model is the MOI, it's an MOI object. You give the JuMP model and it gives you the MOI model. So here, this is pure MOI. We take the MOI model, an MOI function, and the MOI set, and we add it to the MOI backend. And if you ask JuMP, like, what's the model? We said, oh, you created two constraints, this one and this one. And so this one, JuMP would think that he added it, but in fact, you added it yourself. So there is no extra stuff stored in JuMP for these constraints. You just add to the backend. So that's the point I wanted to make. And you can ask, what's the constraint object of? So here you only got the constraint index of the MOI backend. This is just a constraint index of the MOI backend. It's not a constraint reference of JuMP. Basically, when you talk about indices in MOI, we say constraint index, variable index, but in JuMP, we call that variable reference and constraint reference. So JuMP is reference in MOI. So it's an MOI index. And the difference between an MOI index and a JuMP reference is basically, in a constraint reference, you have the index, but you also have the model. And you also have a shape, but I'm not going to talk about this. Okay, so that's basically to explain what's the relationship between the JuMP model and then this MOI backend when you add the constraints. Okay, so any question about this example? Okay. So now, this notebook is about containers. And here I take as an example the variable macro. So suppose, okay, you have a model and you want to create two variables in some container using this syntax. So we'll see in details what exactly JuMP does. So in JuMP, we have three different containers. We have the arrays, which is defined in Julia, and then we have two custom containers, the dense axis array and the sparse axis array. I will explain later. So we always try to build an array because it's the most efficient one if it's possible. Here, in the macro, we can look at the code. We can say, okay, it starts at 1, and there is 2 elements, so it seems we can store it in an array because the indexing just starts at 1. So because of that, we generate a code which creates an array and then fills it. So you don't look at this, I will have an equivalent code just here. So what it does, first it pre-allocates the array to contain all the variables. But for that, it needs to know what are the types of the variables. So in some JuMP extension, you can have variables which have different types than the default one. So variable type of my model gives the types of the variable of the model. So you create an array. The elements are variable ref. And then initially it's undefined. And what's the dimension? Well, there is 2 elements and just a vector, not a matrix.
Where is? Why do you have to use this? So what do you have to do? That's what? You have to do the
So I could just write 2, but JuMP, what JuMP does is it takes all the indices here, and then he asks the length of each of them, and then it's flat because. So I just copy pasted I just copy pasted the generic code here.
Okay. Okay, because so then that tuple would have more elements if you had more indices.
Yeah, exactly. Okay, so next, what it does is it iterates over the indices to fill the array. And so to build a variable, it's a bit similar to constraint, where we did build constraint to build a constraint object, and then add constraints to actually add the constraint. It's a bit the same here. We have this build variable which creates a variable object, and then we do add variable to actually add it to the solver. So first, we had this variable info structure. So what it means, so it's all the information it could get from the macro about what this variable. So first, does this variable has a lower bound? If yes, what's the value of this lower bound? Has it an upper bound? Then what's the value? Has it a fixed value? Then what's this fixed value? And as it the starting value, then what is it? Is it a binary? Is it an integer? That's all the informations. So in this case, it's false for everything because we gave no information in the macro. We just said create variable. We didn't say equal or nothing. Then we build this variable object. So again, there is the error message. If you look at, let's look at what the macro gives. So the macro it gives this thing. And so what this is simply, so it's a function when you code it, it prefixes the error message with the code you call to actually build the variable constraint. So here we just give error. So now we have this variable object. Then we compute the name. So here the name, when you create a vector, it's going to be the name x that's given. And then with the brackets, we make a unique name for every variable. And then once you have the name of the variable object, you actually add it to the backend. So same thing here, there will be nothing stored in the JuMP model, it's just in the MOI model, we add a variable. Okay, so now if we check, we have the two variables created. Okay, so that's for arrays. But then what happens if the user wants some custom indexing like that? So an array is that the indexing starts at 1, so it cannot be an array. So what JuMP will do is it will not recognize the 1 colon something. So it will, okay, maybe it's not an array, but maybe it is. So for example, if you write here indices, and then you say indices equals. If you write this, then in the macro code, we cannot see just from the expression that you can create an array. But then when you actually run the code, you will see that the type of the indices is 1, 2. So you know by the type information, it starts by 1. So you know you actually can create an array, right? So we actually leave this possibility. So what we do is we look at the indices and we say, oh, is the type of the indices based at 1, 2? If that's the case, then we can still create an array. Then if it's not the case, we create a dense axis array. So a dense axis array, it's similar to an array, just that the axes are custom indices. It can be strings or it can be anything. But internally, it's just a rectangular array, just that the indices are custom.
That's JuMP.
Yeah.
Constraint.
Yes, that's a JuMP container.
Similar package called that.
And why not use next to it?
The indexing syntax.
Yeah.
Yeah, there is a subtlety that's it's actually.
So it's not a core thing.
There's an open you can accelerate about for the big one to maintain it and keep what it said.
Yeah, it's very similar, but there's a small difference between axis array and here.
But eventually, this might end up being.
Yeah, maybe if we
replace it on next series. Somebody else might need.
Yeah. Excuse me? Can you speak louder?
The only JuMP right package is kind of awful. That will eventually go away. With any JuMP could use, but I wouldn't use the power secret.
But and the new one, is anybody actually developing the new one?
Yeah, maybe, and maybe some the network trying to work. Like if you touch it with like four touch condition, just collapsing comes over, right? And it's not being bad. Like using those four touch because it's very complicated.
Yeah. So yeah, so it creates this dense axis array, and then it needs to fill it. So again, we make a loop, and here you can see that the user tried to actually use a name for the index, and then this name is used because the lower bound will depend on this index. So it's actually important that this expression, when we use this expression, the I variable should be defined. So what we simply do is we loop over all the indices, and we use this I as a name, so that when you actually call this variable info. This one you say yes, I have a lower bound, it is I. Then the I is exactly the value you want because it's for loop. And so now, again, same thing, you build a variable object, the name, and then you actually pass it to the solver. Okay, so now if you actually ask the lower bound of the variable, you will get the correct. So x, y. Is another
bounds are always good.
Oh yeah, currently in JuMP, everything is float 64. So the last one is sparse assist array. So it's used when the underlying array has not a rectangular structure. So it's a bit similar to sparse matrices, if you want, where you have missing entries, except that's not equal to 0. So for example, if you missing entries, if the function you use to broadcast maps 0 values to something else that value to something else, it will actually fill your array. Because if you broadcast, for example, a sparse array with +1, then all the 0 entries will actually be 1. So you need to actually also broadcast the 0 value. But here it's not the same. Here the missing entries are just missing. There's nothing. So if you broadcast a sparse assist array, it will just broadcast the entries that are there, and the other one just keep missing. So it's like an array with holes. So in this case, it's like triangular array because I goes from 1 to 3 and j from 1 to I. So when you create it, it does not try to do a triangle. It's just like it's the same printing that for dictionary. You print all the indices and then all the values. So what happens here? We know, again, I show a summary. So we build a sparse assist array. So internally it's represented with a dictionary from n tuple 2. So the keys, it's a tuple of 2 elements, the first index and the second index, so I and j. And then the values of the dictionary is variables. And then you fill it. So I, you retrieve from 1 to 3, and j from 1 to I. And then indeed you will just enter the entries you want, and the rest will be missing. Okay, and internally it's like a dictionary. But then we couldn't just use dictionary because, for example, we wanted, when you broadcast value, you need to value dot with the sparse assist array, it should give you value of all the variables. And you don't have broadcasting, for example, for dictionary. So we had to build a custom thing because it's not exactly a dictionary. It behaves like a sparse assist array where the holes are just missing values. Okay. Okay, so that's for containers. Now, talk about JuMP modes. And let me check. For this one, I need, for this info, for this one, you need semi-definite opt interface version 0.5.1. But it's not, the PR in metadata is not merged yet, so it won't work for you. But I use my custom version. So I guess I just need to restart the kernel. Where is it? Okay. If I check. Oh. Yes, that's correct. Okay. Okay, so in this notebook, we suppose we want to solve this SDP problem. So we look at, so this notebook is a bit more about, okay, I suppose I have a solver and I want to write an interface. What exactly should I do? So I take as example CSDP. So the interface of CSDP is you represent the SDP problem like this. So the variables, it's a big X matrix, which is a block diagonal matrix. So when you have a blocks 1 by 1 blocks, it's like variables, and when you have more than a 1 by 1 blocks, it's like PSD variables. You only have non-negative variables and PSD variables. You cannot have, for example, free variables. If you have a free variables, you need to create 2 non-negative variables and say it's A minus B. And that's free variables. And then all the constraints you can have, it's only a fine expression equals something. Yes, so that's what CSDP wants. And if you think about it, JuMP, in JuMP you can represent many different things that are neglected list, and for which you need to do some transformation. Okay, and there is a second subtlety that in CSDP, when you want to enter to provide the problem, what you need to say, first you say, what is the number of linear constraints? And then what is all the blocks? What is all the blocks? What the number of blocks, the dimension of the blocks, and so on. So we first need to pre-allocate everything, and then you can fill the entries. Then you give the entries of A and C and D one by one. So if you think about what I just said before, I was saying that JuMP does not store anything. It directly gives to the solver. When you create a variable, it gives a variable to the solver. When you create a constraint, it gives it to the solver. So here with CSDP, it's difficult because it first needs to know what is the list, what is the number of constraints, and so on. So if you just want to add constraints and you don't yet know what will be the number of constraints, you cannot really do that, right? So there is a gap between what JuMP wants the solver to be able to do and what CSDP actually is able to do. And the question is, what should we do in the wrapper? Okay, so we take an example, which is this problem. So we'd like to know, if you take this quadratic polynomial x squared plus alpha x plus 1, what is the maximum value of alpha such that this is non-negative? Suppose you don't know the answer. So you would write it like that. You say x is non-negative, x11 is the coefficient here, it's 1, x22 is the coefficient here, it's 1, and then x12, it's the alpha over 2. So we want to maximize this. So if you want to write it in the form of CSDP, it would be like this. That's the A1, A2, and that's the C matrix, that's the B vector. Okay, so here it actually works well because what's the problem we need to, we only have like equality constraint and then a PSD variable. So you should need no transformation to give it to CSDP. Okay, so when you run this, it's going to recompile because usually just before I used different environments, we need to recompile every package. Time. So here we use direct model. So what direct model is, it's a way to, so normally if you in the previous notebooks, we used the model constructor here. And this model constructor, it kind of do many things for you. And in these notebooks, I will see exactly what you do. So if you want JuMP to not do anything between you and the solver, you use direct model. In direct model, when you have an MOI optimizer, it just add a JuMP model on top of it, and that's it. It does not do any more things. And you'll see that, for example, for CSDP, it doesn't work. So you create this CSDP optimizer and direct model, so JuMP is directly on top of this optimizer, and then you want to add a variable. And what you have is CSDP will say add variable not allowed. You cannot just add variables because as I told you in CSDP, the interface is such that you cannot just add incrementally things. You need to copy everything at once so that you can check, okay, what is the list of all things you can pre-allocate and then enter the entries. So you think, no, you cannot just add things one by one. You need to use a caching optimizer. Okay. So what's that? So a caching optimizer, it's a buffer. So when you have a solver like that, for which you cannot just add things one by one, you need to copy the whole model at once. It will act as a buffer. So when you add constraint variables, it only add it to this cache buffer. And then only when you call optimize, then it actually needs the optimizer. So it will copy the whole problem at once to the optimizer. And then it will ask the optimizer to solve the problem. So thanks to this caching optimizer, if the optimizer does not support adding things one by one, it's not an issue because JuMP by default, it's always used a cache. And second thing, so even if your solver supports adding constraint one by one, what the cache will do is that if you solve the problem and then after solving the problem, the user add a new constraint, then it will add the constraint to the cache. And then for the optimizer, it will try to add the constraint to the optimizer. If the optimizer say, hey, I cannot add new constraint, then you say, OK, I just empty this optimizer, and I will copy the cache again when the solver asks to optimize again. But then if the solver says, OK, I can add a constraint, then the cache will say, OK, so now the cache and the optimizer are in sync. And so every time the user tries to do a modification, he tries to keep them in sync until an operation is not supported. And then you say, OK, they're not in sync anymore, and I will need to sync it before optimize. So let's use a cache. So here, what JuMP does by default, it has this model which supports every constraint that's defined in MOI. And we can use it as a cache. So we read this model to create a cache. And we create this caching optimizer with this cache and the CSDP optimizer. OK, and then we create, again, direct mode. So we have JuMP on top of a caching optimizer, and then the caching optimizer, we have a cache and CSDP. If we do that, what you'll have is you'll have still CSDP, but now we have a caching optimizer, which is in the state attached optimizer, because currently the optimizer and the solver are in sync. The parent is empty in both of them, so it's OK. But then as soon as you add a variable here, what will happen is that CSDP will say, oh, I cannot add variables, so the cache will be OK. So now the new state is empty optimizer. So the only valid representation of the model is in the cache, and the solver is just empty. And so when you call optimize, you will need to sync them. So the model mode automatic, it's what I have described. So it will automatically empty and reattach the optimizer when needed. If you don't want this to be done behind your back, and automatically you can do the manual mode. And in manual mode, if the optimizer is attached and then a modification is not supported by the optimizer, instead of silently emptying it and not telling you anything, it will just throw an error saying, OK, the optimizer cannot do this. If you really want to modify, you need first to explicitly ask me to reset it to empty, and then I will only modify the cache. So you actually have 3 levels of control. You can either not use any caching optimizer in direct mode, or you can use a caching optimizer in manual mode, and then you can use a caching optimizer in automatic mode, which is the default in JuMP, because it's the easiest one if you don't know what you're doing. OK, so now we add our full problem and then solve. And then now we can see that the optimizer is attached because they've just been synchronized because we needed to optimize. And so at the moment, the cache knows that the cache and the optimizer contain the same problem. But as soon as you will add a constraint or variable, then it will be detached because CSDP doesn't support this. Okay, so you can ask the value of the variable. And so, of course, this call, there is only, the cache doesn't know what's the result of the optimization, only CSDP does. And so the cache knows that for this kind of information, it needs to ask CSDP, because that's the actual solver. But if you ask just information about the model, then it will ask the cache, because the cache has the full and complete model. Okay, so that's the first element that's automatically added by JuMP. If you don't use direct model, it will automatically use a cache. So x squared plus 2x plus 1 is, in fact, x plus 1 squared, so it's always positive. And if you see, you want to use beta, gamma, and it's more than 2. So you may use different weights, maybe by using 1.5 here and 0.1 or 0.5 here, you could have a higher value of 2 here. Let's see. So we need to empty first the optimizer before giving it to JuMP, because otherwise JuMP will complain that you use an empty one. So now, again, we have a cache. But so that's what's not going to work if you don't use the latest version of semi-definite objects. It's actually, it's been merged. So if you update your package, it's going to work. Is it closed? Okay, so what it says is that CSDP doesn't support constraint of the type a find function smaller than some constant. And if you scroll up, you see that indeed you cannot, there is no way in the interface of CSDP where you can add AIX smaller or equal to BR. It's always equalities. So all the affine function should be equal to some constant. You don't have smaller or equal or larger or equal. You don't have that in the interface. And so for CSDP, actually in the wrapper, we don't support that because CSDP doesn't support that. And I support the claim that, in fact, that's the right way to do when you build a wrapper. You should not support things that the solver does not support. Basically, the only constraint that you support is constraint that the solver actually exploits. So if the solver, if it's smaller or equal constraint, it will actually represent this differently in his algorithm, and the algorithm will actually be faster by representing it like this instead of adding a slack, as I will show. Then it's interesting in the wrapper to support this constraint. If it just reformulated into equalities and adding a slack, which is positive, then you shouldn't support that. And the fact that it wouldn't work in direct mode, it's not, yeah.
I tried running that cell and it let me, you did let me do it.
Yeah, exactly. So that's because you're using the semi-definite opt-interface version 0.5. So if you update the version, it won't work. Because I used to add this this support, and it's a lot of code in semi-definite opt-interface, but now I've removed it because we have a breach. Okay, so what we need is bridges. So I won't go into detail, but the idea is that we have in MY a list of recipes of transformations. So here, for example, there is a recipe which says, given a constraint, a find function smaller than a constant, you can transform it into a constraint, a find function equals a constant, and a constraint variable is non-negative. So just by adding so here, what it will do, it will say, so this is equals to some variable, and then the variable is smaller than 2, for example. You just add a slack. And there is a list of, a huge list of transformation like this. And if you use a bridge optimizer, so the full bridge optimizer is a bridge optimizer that knows all the receive that we have in MOI. What it will do is it will, when a constraint is not supported, it will check if there is a receive that can actually transform the unsupported constraint into supported ones. And so here we see, okay, it doesn't support smaller than, but it supports a find function equal to, and it supports added non-negative variables. So in fact, I could just create a slack and then say the slack should be equal to the function. And then it would be a valid form for CSDP. Where are we? Here. Right, so now it works. And actually, it's still, the answer is still the same. So I think this degree of flexibility didn't change anything. Okay, so for more detail about how these bridges are added, there is a video of the last JuMP-dev when I explain it. So basically, there could even be like several bridges that should be used to transform one constraint into a supported one. I have an example where like several bridges need to be used in a row, like 4 or 5. And it actually can find its way, like what's the minimal number of bridges it needs to transform a constraint into a supported one. So that's the heuristic we use. So when there are different ways to transform a constraint into supported constraints, it uses the one that uses the minimal number of bridges, the minimal number of transformation. And that's also a reason why you shouldn't support more constraints that the solver does, because it will make this heuristic less efficient. Because if you do bridge without the bridge optimizer noising it, then this distance heuristic won't work because you did a bridge and it didn't know about. So you think that it transforms the constraint into something that is natively supported, but it's not. So it's better to let all the bridging stuff being done by this guy so that he has the full picture and can do the optimal solution. Actually, what he will we also plan to have a nice debugging where the solver actually sees what are the transformations that are being carried out. And so if everything is done by bridges, you can exactly see how the problem is transformed into the exact representation that the solver needs. Okay, so now there is a last subtlety that I like to talk about here. If you check here, what we did is that we have a cache, and we added the bridge optimizer on top of the cache. So when you add a constraint, it first goes to the bridges and then to the caching optimizer, right? So the issue with this is, for example, if you want to change the solver. So suppose now you like to use SDPA. So first, if you do this, you should get an error saying that set optimizer is not supported in direct mode. So the reason is, so you've created your problem and you have stored the variable reference inside X, right? And in the variable reference, you have, so if you do if you look at what's inside the variable reference, you have the model, didn't expect it there, and you also have the index. So inside your variable reference, you have the index of the solver. And so this index, the fact that the X reference corresponds to this index is the index of the cache of this caching optimizer. Okay, so if you just want to replace all these optimizers by another one, it won't work because it invalidates all the indices that the user has. So when you switch the optimizer, the indices you have need to stay valid. So what we do is, as you see here, it's a direct mode, so it doesn't work. So what we do is we create another caching optimizer. And then, so this caching optimizer, again, we use the same cache, the MY model in JuMP, and we use the automatic mode. And then for this caching optimizer, we add the bridge, which is the bridges, then the caching optimizer, then CSDP, and we use that in direct mode. So that's actually exactly what JuMP would do if you use the classical model constructor. And so the idea is that you first have a caching optimizer, which has in this cache exactly the model that the user built, and the indices of these constraints and these variables in the model is the indices in the variable and constraint reference the user has. So this model needs to always stay, even if you change the optimizer. And then the optimizer of this cache would be first bridges, and then a second cache, and this cache will contain the bridge model. So the second cache will actually not contain the the affine smaller than constant, because this one has been bridged. So the first cache will contain the model built by the user. The second cache contains the bridge model with only constraints that are supported by the solver. And then you have the solver. So you have actually two caches. Right? So if you do it like this, then it says, in fact, the model is not direct mode. It says it's automatic because it's how we would have created the model if you use the automatic method. So it does not actually see that you use direct model. And then in this case, you can actually, yeah, I have not executed the cell. In this case, you can actually change the optimizer. If you want to use no SDPA, then it will work. Because it keeps the first cache is just kept, it changed the optimizer of the first cache. It's okay because the indices, the user indices of the first cache. You can serve with SDPA, it works. Okay, so what's important here is that, in fact, once you have your optimizer and you decide how you write your interface, you can make it so that only one cache is used. So here there is two cache used for CSDP, but you can make it so that there is only one cache. So the idea is that so you have the JuMP model here. You have the first cache, which contains the unbridged model, and then you have the bridges. And then you have a second cache which contains the bridge model, and then you have the optimizer. And you can make it so that this one is not needed. So the reason this one is needed is that when you will copy the model from this cache to the optimizer, the bridges will bridge the constraint one by one. So the model will arrive with constraint added one by one. But if your solver doesn't support that, like CSDP, then it won't work. So it will need a second cache. But if your solver supports adding things incrementally, then it doesn't need this cache. Okay. But in fact, we plan to add support for the bridges to add the constraint in sort of a two-pass ways, such that if the optimizer supports that, then they also don't need this cache. So, yeah.
But that case only happens if you change the optimizer. Right.
But we always have this cache in case you change the optimizer.
Yeah, so, but the case where you need the second cache is only if you solve the problem once with a certain set of bridges, and then you want to change the optimizer and realize, okay, these bridges don't work anymore, right?
Yeah, so that's the reason we need this cache. And so because we have this cache, we need this one if you want to copy the problem implemented. Because when you copy the problem from this cache to the optimizer, remember the CSDP first need to know what is the list of all constraints. And if you bridge the constraint one by one, it won't work. So a plan for the future is that you will have this this allocate load interface, which is described here. So basically, if your solver supports adding constraint one by one, what it does is that when you need to copy the model to your optimizer, what you do is you call automatic copy. Automatic copy, it will, oh, I didn't want to do that. Read this problem, like what are all the variables, what are all the constraints, and then you add everything one by one to your optimizer, and then it's model and the optimizer. So that works if you solver support adding thing incrementally. And then you would say, I support then you say, I support default copy 2. So I support adding thing one by one. And if you say that, if you implement this method, then JuMP will consider that you support adding thing one by one, and so it will not use the second cache if you implement this method. And if your server do not support names, you can say I support the copy if there is no names, because in fact in JuMP all the names are stored in this cache and they won't be copied, so you don't need to support the names if you can by this cache. Yeah.
So the bridges are also added one by one. So if the solver supports incremental model build, then every time you want to add a new constraint, check does it support it? Yes. Add it. No. Add it.
Yeah, it will do that. Yeah. So if you can use JuMP, then the bridges, and then the optimizer with no cache. And it will work with every constraint. For every constraint that added, it checks if it needs to bridges, and then it does. So the cache is not needed for the bridges. Okay, so but then we have this automatic copy 2, which what it does, it first gives you all the variables and constraints, but just for information, just that you can count how many are there and so on, that you can pre-allocate things like for CSDP in the allocate path, and then it will give them again in the load path so that you can actually load the values of the function into the, for example, the values of the CSDP matrices. So if you implement allocate load, you say it here, and then to copy, you use this should be allocate load here. And the idea is that in the future, we plan that the bridge supports the allocate load. So if the cache says, I want to copy the cache to the optimizer, the bridge will say, hey, do you support allocate load? Do you support like default copy 2? If yes, OK. If no, do you support allocate load? If yes, OK, I can do the allocate load. So all the constraints will be first passed in the allocate path. So there will also be bridge in the allocate path so that it can count what are the things that are in the model, and in the load path, they will actually be loaded. So they will actually be bridged twice. But then you don't need this cache. So we'll only need this cache if you do a custom copy 2, which is not allocate load, neither default copy 2, because then the bridge don't know what to do with it. Is a second cache. Okay, so so that's an important question when you implement and you MRI implementation is, do you want to copy thing in the automatic copy 2 way? That's what you need to use if your solver supports actually incremental loading. And if it doesn't, then maybe the most appropriate way is the allocate loads interface. Yes?
There's a straightforward way of knowing whether my model currently uses bridges, and if it does, what transformation it did. So to come back to the example that you gave where you have the x plus y does indeed,
yeah.
if I have a solver that only takes the constraints, and I can have a bridge that automatically adds a slack.
Yeah.
And then my solver will only see one equality constraint with this slack.
Yeah.
But from JuMP, I don't see that transformation. Is there a straightforward way of knowing that?
So currently not yet. You can go inside the bridge optimizer and look at the list, but we plan to add like debugging facilities, maybe even like a graph of the bridges and stuff like that. But it's not there yet. But it's definitely a planned feature. And also sometimes when you add a constraint, it says not supported, but it's not clear what's missing. Because sometimes you could apply a chain of bridges and there's only one thing missing somewhere, and you don't know exactly what it is. And we're missing also a debugging facility to say, okay, why is it not supported? What's missing exactly? Is it almost supported, and is it only one thing missing, or stuff like that? And that's particularly useful when you implementing a bridge. Okay, so that's the idea. What do I mean by this cell? Yeah, so if you use directly, so that's, yeah. If you use directly, you don't use this cache currently with CSDB. So you do it like this. So I have the optimizer, then directly the bridges, and then a cache. If I try to solve the problem, what he will do is when he will try to copy, then he will say, oh, do you support, the bridge will say, do you support automatic copy? Do you support, since bridge doesn't support allocated yet, he will just say, do you support allocated copy? And if it says no, then he will say, okay, I cannot do this copy, and he will say, I don't support copy. The bridge currently only support copy if below him there is a layer that supports automatic copies, which is the case for the cache. But later it will also support allocated. Right. So here I've taken Mosaic because in Mosaic actually you don't need any cache, because the Mosaic API you can add things one by one. And so if you can just use Mosaic and then just a bridge, no cache nowhere, and then it will work. So that's the example over here. With Mosaic you can just do. But by default, if you use Mosaic with JuMP, by default JuMP will use a cache here, and then the bridges, and then Mosaic. And this cache will be there just in case you want to change the optimizer. And if you want to not use this cache, then you can use the direct code. Okay, so okay, so that was about the caches and the bridges and how they interact with JuMP now. All right. Let's see now what are the MOI attributes, right? So here I have the typical structure that I've detailed here. So suppose you have JuMP and then a caching optimizer with a cache, and then a bridge optimizer, and then bridges, and then maybe directly an optimizer. Okay. So there are 4 types of attributes. There are optimizer attributes, model attributes, constraint attribute, variable attributes. So a constraint attribute, basically, it's an attribute for which you need to give the index of a constraint for it to make sense. For example, a constraint name if you ask for the constraint name with a constraint index, it doesn't make sense. Same thing with variable attribute is an attribute which makes sense only when it's coupled with a variable index. And the model attribute, it doesn't need to be coupled with any index. And an optimizer attribute, it's when you can think of it as like the parameters of your solvers, like the maximum number of iteration and so on. So it does not actually affect the optimization problem. So it's not like the number of variables and so on. It's not about what's the model, but it's more about how the solver actually going to solve it. So it's like parameterization of the algorithm. Okay, so that's the 4 category, and then there is two traits for attributes. There is the is set by optimizer and is copyable. And so it's important if you want to define a new attribute to know in which trait it belongs to. Otherwise, you will not behave correctly. Okay, so the is set by optimizer is an attribute that's actually is not going to be set by the user, but when the user call optimize, then it will be set. For example, it's the primary value of a variable. The user does not set the primary value of the variable. When it can optimize, after that, it can say, OK, what's the primary value of the variable you found? Same thing for the dual of constraints, for instance. It's set by optimize. Or the termination status, the primary status, the dual status, all these are set by optimize and not set by the user. And for example, if you say constraint name, this is not set by optimize. It's the user that sets that. Or the objective function, it's not set by optimize. It's the user that decides this. Okay. So we have these two categories. And the second is copyable. So this is attributes that are actually going to be copied when you do a copy operation. So for instance, the number of variables, you do not copy this attribute. It's like implicitly copied when you copy the variables. So you can ask what's the number of constraints, but you cannot set the number of constraints. It will be set indirectly when you add variables. Same thing for the list of constraint index, the list of variables, the number of constraints, and things like that. Okay, so there is attributes that you set, and some attributes that are set by optimize, and some attributes that are like implicitly set. Okay. So I've looked at all the different possibilities. So here are the optimizer attribute. It is the model, variable, or constraint attribute. And here is it set by optimize, and is it copyable? And in fact, I could fill 5 of the categories. The other, we don't have example yet. So if you want something that's not set by optimize and not copyable, and it's an optimizer attribute, there is a solver name. So every MOI implementation should set the solver name, which is like what the name of the solver. So for CSDP, this is CSDP. And this is used in the model printing, as you've seen. Here, solver name mosaic. And it's actually queries the solver name attribute. So it's not going something that is set. You cannot set the solver name. It just, when you create the optimizer, it has a name. Okay. Oh. And then something here. So we just added a new attribute because it was a common query when we released is the silent attribute. The silent attribute is an optimizer attribute. So it doesn't affect what's the model, but it affects what's going to do, what the solver is going to do. So if you say silent to true, it means the solver will not print anything. And if you do not set silent, that the solver should by default print. Like usually in solver, it's like log level equals to 1. That should be the default. Even if the solver is not the default for the solver, and some solver by default prints, and some by default do not print. And we have the convention that by default, the wrapper should set that the solver should print, and then the user can set the silent attribute, which is the same attribute for every MOI wrapper. It's a solver independent one, and when you set it to true, then the solver don't print anything. Okay, so this one, it's not set by optimize, but it's copyable. you can actually set it, right? So when you set it to a model, it will be copied to the optimizer. When you set it to the cache, it will be copied to the optimizer when you give the optimizer. Okay. So now, for the non-optimizer attributes, for those that are not set by optimizer, not copyable, it's the one that are like indirectly set. So for example, the number of variables, you never set it. It's not the optimization that finds it. It just, when you add variables, it defines it. The objective sense, it's not set by optimize, but then it's you that needs to set it. It is going to be copied between model explicitly. And the variable primal, it's set by optimize. So when you optimize your model, you get a primal back. Okay, so when you create four types, and then you should implement these two methods to say exactly what it is. Okay. The time limits optimizer attribute. So by default, is set by optimize is false. So if it's false, you don't need to implement the method. And is copyable, it's the opposite of is set by optimize. So if you look, if you are in these two columns, then you see that is set by optimize and is copyable are the opposite. So if it's the case for you, you don't need to implement is copyable. And if set by optimize is false, so if you are in these two columns, you don't need to implement is set by optimize. So only variable primal need to implement is set by optimize, and then this one needs to implement is copyable equal false because it's not the opposite of. Yeah. So we like to create a time limit attribute which set the time limit for the solver. So if you say 2, it means after 2 seconds the solver should stop what it's doing, even if it's not found the solution. So suppose we create this attribute, we check is set by optimize is copyable default values. Okay. So now we'd like to set it. So what happens when you set an attribute? So if it's an optimizer attribute, so suppose you are in this situation, you have JuMP, the cache, then bridges, then the solver. If it's an optimizer attribute, you will both set to the optimizer and the model. So even if the optimizer doesn't support incremental loading of the constraint of the variable, it should at least support incremental loading of the optimizer attribute. It's just parameters, right? So that optimizer attribute, it will not be copied at once. It will be given one by one when the solver or the user sets them. And for the other attributes, they will be set to the cache, and then it depends on the state of the caching optimizer. If currently there is no optimizer, then it's just to the cache. If the optimizer has states empty optimizer, it means they are not in sync, so it will just be set to the cache, and then it will be copied when optimize is called. And if currently they are in sync, so the state is attached optimizer, then it will try to keep them in sync. So for example, suppose the attribute is like the objective function. So the user wants to change the objective function. So what he will do is he tries to change the objective function of the model of the cache. It will of course work. And then it will try to do it for the optimizer. If the optimizer say, oh, you cannot change the objective function on the fly, it needs to be copied at once, then it will say not allowed error, and then the caching optimizer will say, okay, no, they are not in sync. I will set it to empty optimizer, so that's in the automatic mode. In manual mode, it will throw an error saying, okay, you need to detach them manually. Yeah, so that's the case for adding variables and constraints, but also for setting attributes. It's just the same principle. And then if it's detached, then when you call optimize, they will be resynced. And when you get an attribute, then if the attribute is an optimizer attribute, or if it's set by optimize, it will ask the optimizer, because the cache has no idea what's the primal value of the variables. But otherwise, it will ask just the cache. So if you say what's the objective value, objective function, it will ask the cache. If you ask what the objective value, it will ask the optimizer. Okay. So let's try. I use mosaic with a cache in automatic mode, and then I add the mosaic optimizer. I set it to the cache. Currently, the cache is empty optimizer because when you create it, there was no optimizer, so it was empty, and when you reset, it's left empty. Time limit, but we've already defined time limit. Don't need to execute this cell. So suppose you set time limit. It says unsupported. So it says that because mosaic doesn't support, because it's an optimizer attribute, it's not just set to the cache. It's immediately set to both, right? Because when you get an optimizer attribute, it will ask to the optimizer. So the optimizer should always be in sync for the optimizer attribute. So because it's an optimizer attribute, even if the state is empty optimizer, it will set it to both. And then mosaic will say, oh, I don't not support this new attribute. So when you create new attribute, usually because some server supports that. So let's add the support for it. So we say, first, mosaic supports the attribute. And second, we say, how do you set that? So in mosaic, this is kind of server dependent. You need to say this is a double parameter with this name. And how do you get the attribute? And then know if you set it and get it, it actually works. Yeah. So now it's actually set to mosaic, even if the state is empty optimizer. Okay, so now support that you change the optimizer. You say, no, it's CSDP. Okay, so immediately when you change the optimizer, the cache will immediately try to copy all the optimizer attributes. It will not try for the full copy to be done. The optimizer attributes are always in sync. And so immediately it says, oh, CSDP doesn't support time limits, so I cannot attach it. Okay, so it's empty, but still it has tried. Let's remove CSDP. So now we set the time limit, but there is no optimizer attached. So what it does, it just sets the time limit to the cache. And then once, when you empty optimizer, it's mosaic, it should keep the optimizer attributes. So when you empty an optimizer, you remove all the variable, all the constraint, but the parameters, you keep them, right? So now we attach mosaic to the caching optimizer, and then immediately it sets the attribute. And if you ask mosaic, the time limit is 1, right? So that's just how it works for the optimizer attribute, but I explain here all the cases, so that's an example. Okay. So now, so that was how attributes plays with cache. Now, how do attributes play with bridges? So that's a bit simpler. It's basically when the attribute is a constraint attribute and the constraint is bridge, then it will actually be redirected to the bridge. For example, if you ask the dual of a constraint and the constraint is bridge, then you cannot ask this to the optimizer because the optimizer doesn't know about this constraint. So you ask it to the bridge. And so the bridge, what it will do, it has normally created other constraints, and it will ask all the other constraints what their dual is, and then it will try to invert the transformation to get the dual of the transform constraints. So when it's a bit tricky when you define a bridge is that you need to explain how to transform the constraint, but also how to transform the dual back and the slack back and so on. And also the starting value and basically any constraint attribute. So here we just take a constraint that is not supported by mosaic so that it's bridge. So here it's a BSD constraint, but it's a mosaic only supports PSD variable, not PSD constraints, like an affine function inside PSD. So what it will do is it creates slack variables, and then it will say this expression is equal to the slack, and then the slack should be PSD. So this will be bridged. And then you can actually ask if it's bridged. So you ask the bridge, like you give the MY index, and it's only dependent on the type. And this type of constraint is always bridged. And you can actually look at what is a bridge. And you say it's a vector/bridge. Bridge. Right. So we optimize. And then we want to get this constraint attribute, which is set by optimize. So it will try to ask for the bridge. And just to show you that it tries directly to the bridge, if you try to get it, it will actually say it's the bridge that does not support these attributes. Maybe the optimizer does support it, but the bridge does not. So that's the reason it doesn't work. Right? So that was how to define an attribute and how it interacts with cache and bridges. Yep.
So if you have a solver-specific constraint actually is set by optimize, that won't work.
It works if the constraint is not bridged. So if the constraint is not bridged, it directly goes to the optimizer. But if it's bridged, then it needs to add the bridges. Right. Okay, last one. Something else you can do is define new set and function, and then new bridges. So suppose you have, so this is a very simple example, not very useful, but you can come up with a useful example. I've chosen a simple one so that the notebook actually is simple. And actually taken for a test using JuMP. So basically, when you have a solver, it may happen that the solver supports some structure that is not defined in MOI. Right? It supports some special set, and actually it can solve more efficiently if you have constraint in some set. And even if you can transform this set into other constraints, then you don't want to do that, because in your solver, if the user is able to actually provide you with this structure in the problem, you can solve it more efficiently. So you would like the user, which is on one side using JuMP, to be able to inform you about some structure of the problem, and you are on the other side in the solver. So how do you do that? So here, the example is a bit silly, but I took a simple one. It's, suppose you have this new set, which is the non-negative numbers. So we have non-negative, the vector set of non-negative. We have the scalar set of greater or equal to a constraint, but we have not a scalar set of non-negative. So this one is easily transformable to non-negatives and greater than, but so that's what we consider. So suppose the solver supports that. And then if you want to model this, to use this set in JuMP and being transformed to the solver, you don't need to do anything. If the solver says X is non-negative, it will just work. The constraint will be passed to the solver, and if the solver supports this new constraint, it will just work. So if you have a custom constraint, you can just define it in your MOI implementation, and when the user will use it, it will directly be able to constrain you to create constraint of this type in JuMP. You don't need to do anything. You just need to do this function in set syntax. So in this case, well, GLPK does not support it. So suppose you have this solver that has this custom set, and then so the user, he'd like to use this custom set to use when he uses the solver, but then if he use that in his code, then when he will switch the solver, it won't work. So we'd like to use this set, and then if this is a solver that does not support it, then it transforms it to something else. So that when you use this code, if it uses a solver that can exploit this new structure, then it exploits it. Otherwise, it just reformulates it. And then you can benchmark it, actually, this is interesting or not, and stuff like that.
How does JuMP know which bridge to use if it's a custom set?
So that's a good question. You need to you need to define a bridge, but then JuMP will not know about this bridge, right? And you need to manually add the bridge. And you can actually extend JuMP so that it automatically adds the bridge when there is a non-negative constraint. That's what we would see. So here we defined the bridge. So how do you define the bridge? First, you need to create a bridge object, which is an abstract bridge. Okay, so that's the receipt. So the object will basically contain information it needs about what is the output of the transformation. For example, he needs what he will do is he will bridge the constraint, some function is non-negative into this function is greater than 0. That's the bridge. It's a bit trivial, but and so it will remember this constraint index because when you delete this constraint, you also need to delete this one first. So you need to actually remember the constraint index to delete it. And also, if you that's all you need to remember. Okay. So the constructor of the bridge will be the transformation. So in the constructor, you have the model. Transformation. So you add this function in number is greater than 0, and then you create your bridge with the index of the constraint created. Okay. So then once you do that, you try, as you said, it doesn't work because JuMP doesn't know about this new bridge. So what you can do, okay, so here first, first you need to actually, in your bridge, you need to actually say what the bridge supports and what it doesn't support, because as I said, JuMP will try to automatically find which bridge to use. So it will have, okay, so GLPK supports this function in greater than, but it doesn't support this function in non-negative. It needs to actually figure out that this bridge is going to do the bridge. It will not try every bridge and see what constraint I created. That's not what you do. So you need to say what the bridge supports. So here you say the bridge supports bridging scalar function in non-negative. Okay, and the other one it doesn't support. And then you need to say what is the bridge, the type of the bridge that's created when you add some scalar function in non-negative. So here, if you add some scalar function of type f in the set non-negative, it could create a bridge of type tf. F here is the, if you look up, f is the type of the function created in greater than. Here is the same type because we don't do any modification to the function, right? But it could be different type. For example, if you need to do this function minus some constant, then if this is scalar variable because you need to subtract with some constant, it will become an affine function. So here you may need to use. So we have in NameY we have function called promote operation here. And promote operation, you say the operation you want to do, for example, subtract or add, and what are the functions involved. They will give you what's the result of this operation. And it's not using Julia inference. It's not like some of you may know promote op. Promote op, you give a Julia function, and then you give the argument, it try to infer what's the return type. It's not the same. It's more like promote when you actually need to say, you need to define a method for promote operation for every type. So it's more like promote than promote op. So it's completely safe to use. And then once you have the concrete type of your bridge, you need to say what are the added constraint types, because so then what the bridge optimizer will do is say, okay, there is this bridge. It supports bridging the constraint that needs to be supported. And then it needs to add this kind of constraint. Oh, GLPK supports that. Okay, I can use this bridge. And bridging this constraint to GLPK, we only use one bridge. So this kind of define an edge in a graph where, so you can consider a graph where every node is a pair function set. So you have a node which is single variable
in non-negative. And then you have a node single variable in greater than. And then you have a node scalar affine function in non-negative. And then you have a node scalar affine function in greater than. And basically the bridge will be to these two edges. Okay, so here you kind of define these two edges, which mean from this one I can bridge it to this one, and from this one I can bridge it to this one. But in fact, it's defined an infinite number of edges because the function can be any scalar function. So if someone creates a new scalar function, the bridge will also work with this new scalar function. It's not specific to scalar function that's created in Y or anything. Okay, so what the bridge optimizer will do is this one ever costs 0 because you need 0 bridge to bring them to something supported by JuMP. And then using this, it will deduce that this one ever costs 1 because they need only 1 bridge to be bridged. Use kind of a Bellman for algorithm to kind of find the number of bridges we need to bridge this node. And then even though that costs more than infinity, it can be bridged, bridge using the path that's fine like this. Okay, so that's kind of the edge information in the graph that you need to implement. And then that's what I want to say. So when you want JuMP to say automatically add this bridge, when the user build a constraint function in non-negative, so remember build constraint, I talked about this in the first notebook. So when you use the constraint macro, it uses this build constraint to build this constraint object, right? So that's the place where you can actually say it should be bridged. So you define the new method. So this is not type piracy because non-negative is all types. Even if build constraints, it's a JuMP type and this is a JuMP type, this is all type. So we define a new method for JuMP, but it's completely safe. It's just that when the user use non-negative, like here, automatically we call this method. And then what JuMP normally do is just create this scalar constraints with the function and the set, and we wrap it in a bridgeable constraint with the bridge. And so when JuMP, after that, JuMP, what he will do is he will give this constraint object to add constraint. So add constraint, you will first see, oh, a bridgeable constraint. So it will add the bridge, and then it will add the constraint. Okay, so you can pack the bridge in, you add an information on it, like a post-it, say, hey, you have also this bridge you need to add. So bridge will JuMP will automatically add it. So if I execute that, too, 5, 6, yes. But not this one. It's number 2. Then I have not executed this one. Not even this one. Okay. Now it should work. Yeah. So now the bridge is supported. So it actually can store the bridge in the model, in the cache. And in fact, so now it should work. So if the solver supports this constraint, it works. And if the solver does not support this constraint at JLPK, it will automatically be bridged. So there are a few more things that you need to do for your bridges. For instance, now if you ask JuMP, what is the number of variable in greater than constraint, you would say 1. So for the user, it's a bit weird because he never had a constraint like that. He added a variable in non-negative, not a constraint like that. So the constraints that are bridged, you actually need to, the bridge will need to tell the bridge optimizer that he created something that should be hidden from the user. So you need to implement number of constraints and list of constraints indices to say what you've created so that actually they can be hidden. So now that you implement that, the JuMP will say, no, there is no variable in greater than constraint created.
Okay. So next, if you want the dual or primal value of a constraint, it won't work because you've not implemented for the bridge. So it's an example of constraint attribute, as I told you in the previous notebook. If it's a constraint attribute, it needs to be, and it's a constraint, it's a bridge constraint, it needs to be implemented for the bridge. In this case, this is not implemented. So you can implement constraint dual, constraint primal, and then you can get it. Last but not least, you need to implement deletion of your bridge. So if the constraint is deleted, you also need to delete the constraint you've created. Okay, so you need to clean behind you. And for this, you just need to do that. And now if you ask number of constraints, not there. But this time it's not hidden, you just delete it. Okay, that's all I wanted to say. Thank you very much.
So this kind of concludes the formal part of the workshop today. For the remainder of the day, we'll be collaborating. What's that? Oh, yeah. So that is we have a formal coffee break and then we have lunch.